I mean, whatever you got to do for the squirrels, right? I feel like, sacrifice for the greater good. All right. So we are going to, I was a little mixed up kind of going into planning of this week, but should be fine. This first section is going to be a little bit disconnected, I would say, from the rest of what we're doing. It like geometrically, very tangentially plays into a little bit of what we will see. But really, I would say we're going to start the bulk of kind of our like circle implementation stuff with like the gradients and whatnot. We'll mostly kind of start implementing and applying that tomorrow. Today, what we're going to do is something that used to be what we covered in Unit 1. We swapped this out for absolute value functions and inequalities this particular year. Yes, you have the packet. So we swapped it out for the absolute value inequalities and functions, and are going to hopefully be able to kind of round out all of what we have. So a little bit of a weird blurb, but should be in a pretty good spot here. And to be honest, this is one of my favorite lessons to go through. I think the ideas flow relatively seamlessly from one to the next. And they start with incredibly intuitive understandings of just like how the world works. And so I think it's really fun when you get to kind of start with a very basic notion, kind of common sense, and work your way up towards something that looks very, very impressive, although again, is really just going to be an application of this common sense. So the first thing that we are going to discuss is the idea of distance. And we are going to lead off with kind of a base case here, which is going to be distance in one dimension. So one-dimensional distance, or really just like if I am on a number line, how do I convey the idea of distance? So let's say I want to know the distance between 2 points. We'll say one point is at +2. We'll say one point is at +7. What would you guys do to go ahead and find? Why did Sophie do 7 minus 2?
Was there only 2 points?
Okay, yes, there are only 2 points. Why 7 minus 2? I know 2 minus 7.
Because 7 is the bigger number.
And subtracting the bigger number, having the bigger number first, it's going to do what? Keep the number positive. Okay, so an important thing about our distance here, and kind of something very fundamental that we are going to see, is that our distance must be positive. The way that Sophie did it was great, where we arranged the larger number first. That will work very well for us if we do this. So 7 minus 2 would give us that there is a distance here of 5. Let's say maybe rather than being given these kind of discrete values where we can kind of use our understanding of where these numbers are relative to each other, let's say instead that we're trying to take the distance or trying to find the distance between 2 points where we don't necessarily know their relative values. Conventionally, the way we would read this is that A is the smaller value, B is larger, but we don't need to follow that convention. That is certainly not necessarily a given. And so what could I do here in order to find the distance between A and B if I don't necessarily know if there isn't a given between which is going to be bigger than B? So we're still trying to do this thing. We still want to do 7 minus 2. Like that would be B minus A, but that's only true if B is bigger than A. A could be bigger than B. And so what could we do to kind of force our answer to still be positive while maintaining this idea of distance? We could use the absolute value function that we kind of built, right? So we could say here that I do want to take A minus B. That could be a positive distance, or it could be the negative kind of equivalent of our distance. And so taking that value and taking the absolute value of it will guaranteed give us that positive value that we are looking for without changing the, what we might describe as the magnitude of that distance. And of course, we could have also arranged this as the absolute value of b minus a, and we would have gotten absolute value of b minus a, and we would have gotten the exact same thing, right? In this case, the order really does not matter. It doesn't matter what you're subtracting first or second. One of these is going to be a positive, the other one's going to be a negative. We're taking the absolute value right now. The problem we run into with this, really not necessarily a problem, but I'm going to present it as a problem, and that's that the absolute value function kind of sucked. It was actually, when we started breaking it down, fairly complicated. It had like the piecewise definitions and all of that kind of mess. And so this is a completely valid way to define distance in the one dimension. I would like to come up with an equivalent way to do it that lets us kind of sidestep some of the obnoxious stuff that we might have to deal with absolute value. So absolute value, great way to guarantee that our stuff is going to be staying positive. Also makes it so that the magnitude doesn't change. That's really important. The size is going to be staying the same. What else could I do to guarantee that this subtraction gives me some kind of positive result? What else could we do here other than take the absolute value?
Just do b minus a.
But again, we don't know that b is bigger than a, and we don't know if a is bigger than b. We can't make those.
Oh, it gives the distance from.
That's what we're working towards.
But yeah,
We'll get there.
you know.
Currently, we're in one dimension, so distance formula would definitely be overkill here.
Yeah.
Our goal here, we want to do a minus b or b minus a. We want to guarantee the result to be positive, but we don't know which one's bigger than the other. And we want to kind of stay away from absolute value just because it's a little bit messy. What could we do? What's something we could do to a number that's going to guarantee make it positive? Yeah, we could square it. That'd be a really good way to kind of force everything at the very least to be positive, right? So maybe instead of the absolute value of a minus b, we take a minus b and we square it. We could do b minus a and square it as well, right? Absolutely. That's definitely going to give us a positive value. What's the issue that we run into when we just start going around squaring numbers all willy-nilly? It's not going to be the actual distance, right? It's going to be a different value. If I square a number that's larger than 1, I now have a larger value than my distance. If I squared a number smaller than 1, I would now have a smaller value. So we run into the problem that, yes, this gives me the desired positive result, but it isn't giving me the actual distance. What then could I do to take the now positive value that I have calculated and resize it back down to the actual distance that I got? We're going to take the square root. So we square the distance in order to force it to be positive. We then take the square root to reduce the size back down to a value that is actually reflective of the distance. This is actually equivalent to taking the absolute value. I did 1 minus 4. That's -3. If I square -3, that gives me +9. Take the square root of 9, that gives me +3. It accomplishes the exact same thing as taking the absolute value of 1 minus 4. And we're going to see for the formulas that we're going to be working with, this is actually a fairly nice, compact way to accomplish exactly what we were trying to do. Could we have done this with absolute value? Sure. There's nothing wrong with doing this with absolute value, but we'll see that the formulas actually simplify very nicely when we reframe absolute value in this. So distance, we can generally think of as taking like the difference between our 2 points. We run into the issue of we want to guarantee the thing is being positive. Yes, we could accomplish that by taking the absolute value, but kind of a neat way to be able to do this. It feels like it's a little bit extra for what we are looking at here, but what will end up being a very compact way to do this is we could square the difference that we have and then take the square root to reduce the value back down to what we were seeing. But this is effectively to just kind of ensure that what we are looking at is a positive difference. Questions in the one-dimensional case. So just on a number line, finding the distance between two values. I would say the seed from which we are going to derive everything. So if we feel good about this, then hopefully everything else also fits pretty squarely within the framework that we're going to be building. Questions? Okay, that's one dimension. That's not too bad. Let's make it a little worse. Let's take this and let's scale it up to 2 dimensions. Let's say I want to. This is really more akin to the kinds of questions that we are going to be asking ourselves. Very commonly, the kinds of questions that you might see on, like, I don't know, like the ACT or something. Let's say I've got a point here. We'll call this point, let's see, it'll be -4 and 3. And we've got a point here, which we will call 3 and 1. And I want to know, again, the distance between these points. Okay, so our trick here is going to be really, can I reframe this question based on information that I already have, based on stuff that we have already done? Can I rewrite what we are seeing here, not in terms of 2-dimensional distance, but instead in terms of 1-dimensional distance? Rather than traveling straight from point A to point B, could I instead take perhaps a more circuitous route to arrive there doing 1-dimensional movements instead? What would you say? Okay, so Pythagorean theorem, we're implying some kind of like a squared plus b squared equals c squared, but where's the triangle? How would you construct a triangle here? Okay, so we've got some kind of vertical displacement that we could do here. So from -4, 3, maybe just straight down. So the x value is going to stay the same, but we want to now match to the y value that we'll have here of 1. And then similarly, x displacement all the way across. So a right triangle like this. This is a fantastic way to take what otherwise would actually be a fairly tricky question and reframe it in such a way that now we're just dealing with 1-dimensional movements. And then we're going to use some applied Pythagorean theorem in order to actually find the distance that we want to travel. But first and foremost, we can think of this movement as some kind of movement in the x direction, some kind of movement in the y direction. Okay, how can I find my movement in the y direction? What is that, in this case, what is that displacement going to be? It's going to be 2. We started at 3, we ended at 1. How far have I moved? Obviously, we have moved 2. In order to kind of communicate that distance, we could have used our 1-dimensional distance formula, where we could say, maybe do like 1 minus 3 squared, and then take the square root of that. Right, which would just be 2. Same as the absolute value, right? 1 minus 3 or 3 minus 1, whatever. Order here really doesn't matter at all, because everything's going to be positive regardless of what I do anyway. So it really does not matter. And then similarly, from -4 to +3, intuitively, we know how far that's going to be. What's that distance going to be? From starting from -4, ending at +3. We've moved 7, and we can show that by, again, taking this square root of 3 minus -4 squared. Again, order here does not matter, but it gives us this displacement of 7. I could have done -3 minus 4. Again, this weird absolute value gotten the exact same thing. Okay. And so our Pythagorean theorem here, a squared plus b squared equals c squared, we have that a is 2, that b is 7, is going to be equal to c squared. 4 plus 49 gives me 53, and ultimately I'm not looking for c squared. We again have to adjust. This is the square root of, in this case, 4 plus 49, which gives us the square root of 53. So we should say, rather, this distance is the square root of 53. Okay. You'll notice here that the actual kind of formulaic bits get to looking a little bit messy. Again, that's kind of us trying to sidestep absolute value. Actually, we'll see that the formula itself doesn't even require us to sidestep absolute value, but a lot of this will cancel when we actually like start plugging into formulas here. So when we are looking at the kind of really large subheader of distance formula, it's going to feel very complex. In fact, it is really not. We are looking at some kind of y displacement. We are looking at some kind of x displacement. Those are forming the legs of a right triangle, and then we're just doing Pythagorean theorem with those. Okay, that's all well and good when we're able to like combine terms and when we actually know specific values. What this means in terms of a generic formula, though, again, gets to be looking a little bit messier. If I have 2 points, we'll call this x1, y1, and x2, y2. Again, I don't necessarily know the relation between these points. The ones I have drawn are in quadrant 2 and quadrant 4. That does not need to be the case. I could orient this in any way really that I want. But in order to find the distance between these points, we again are going to be constructing this right triangle. Where our y displacement can be found either with absolute value or by squaring the difference in my y values and then taking the square root. And my x displacement can be found by doing the exact same thing with my x values. And again, here, whether it's x1 minus x2 or x2 minus x1, the reason why we are squaring it and then taking the square root is so that that order doesn't. I could mix these up. I could mix these up. I could do y2 minus y1 and x1 minus x2, which I've generally said don't do that because it matters in a lot of cases. Here, it really does not matter, which I do. You should be totally good. And with our Pythagorean theorem, the idea that our distance squared is going to be equal to our a squared plus b squared, which in this case, our square root of y1 minus y2 squared. squared plus our x displacement squared. Again, looks really, really messy, but the framing here, the reason why we did exactly what we did is because the square root and the squared cancel very, very nicely. And we end up with, for our distance formula, that the distance squared, c squared, is going to be our y displacement squared plus our x displacement squared. Yep. The whole top bit, or yeah. Which is just Pythagorean theorem, right? Very, very literally a direct application of Pythagorean theorem, where again, this is just the absolute value of my y displacement. This is just the absolute value of x. Okay, this would be a fantastic place to stop with distance formula. This would be great. This is totally fine. Ultimately, though, if we're needing to find the distance, what would I need to do to both sides? I need to take a square. Okay. So generally speaking, when we actually write the distance formula, we're going to represent it as, rather than d squared is equal to something, we represent it as that d is equal to the square root of all this mess. And in particular, it is the square root of our y displacement squared and our x displacement squared. Right, but really, this is just a squared, this is just b squared, and this is just c, right? I could do the exact same thing with the Pythagorean theorem. And you get the exact same. And intuitively, we generally don't need to plug into the formula. Normally, we're able to actually do these computations without it. We will see that the formula is going to then give us a very nice kind of direct way to get to the circle formula. But when we are actually using the distance formula, kind of keeping this intuitive notion of one leg is going to be x displacement, one leg is going to be y displacement, is generally enough to figure out what is going on. And actually, I'm not ever really going to ever be like using this formula as it stands by like plugging things into it. You'll see what I mean here when we look at our first example. Any questions here, kind of preliminarily, before we look at example one with what we've derived here, this kind of application of Pythagorean theorem or our two-dimensional distance formula? All right, let's take a look at example one then. In this case, we are asked to figure out the distance between points that we have been given. I'm going to take a stab. Let's do B together, and then I'll give you guys a little bit of time to work on A and C. I picked the easy one for us to do, but that should be totally fine. If you want to, you could go through and plug all of the x's and all the y's into the formula. That's totally fine. But again, let's kind of try and do this more intuitively. I think that that's actually fairly straightforward here. If I'm starting at the origin and I'm ending up at an x value of -3, what is my x displacement here? Displacement would be 3. the distance in terms of the x direction that I have traveled. I have traveled a distance of 3. Maybe distance is a better way to say it than displacement. Displacement can be positive or negative. Whatever. We'll say distance, right? I've traveled an x distance of positive 3. And in terms of my y distance, how far have I traveled in the y direction, starting at 0 and ending at positive 4? I have gone up by 4. Legs of a triangle have to be positive. Okay, that's kind of another part of this. Intuition, distance doesn't make sense. Noticing that this is a special kind of case for our triangle, you absolutely could do that. But let's say that we didn't remember that this is a special case. We know that a squared plus b squared is equal to c squared, or that 9 plus 16 is equal to c squared, which gives us that c will be the square root of 25. So just identifying how far have I traveled in the x, identifying how far have I traveled in the y, and then those are the legs of your right triangle. Take a stab at A and C. So trying to figure out the distance that we get between these values here. Between these points, rather, I should say, not just. How'd you get? This one looks good. I will, yeah, this one looks great. For this one, how'd you get the root of 4 here? So I agree with your triangle. So what would a squared be? 3. What would b squared be? Yeah. Yeah. Otherwise, it's agree. Right. Yeah, exactly. Exactly. Yeah, that's your distance. How far have you traveled in the x direction? Yeah, but in this case, we're just thinking how far, so we don't need the pi. It'll always be positive. Which, when you square it, it would be positive anyway, which is why this kind of making sure that it's positive then this might be a little bit overkill, but because the Pythagorean theorem fixes that for us, but whatever. From 2 to negative. Otherwise. And then from, yeah, same, -3 to 1. From start to end, how far have you come? This looks good. Make sure you are squaring these values. Yeah, yeah. I just need to write it. Okay, perfect. And then you're gonna take, when you take the square root, you're gonna take the square root of the sum. So you need to add them first, and then you take the square root. So you would do 64 plus 9, and then you would take the square root of that, which is gonna be an irrational number. So you would just leave it as like the square root of 64 plus. All right. Yeah. What's the distance from negative? So whenever we're doing distance here, we're always going to subtract. So -3 minus 5 to go from -3 to positive. Looks good. Looks good. Yes, quick. Well, how far do we have to go from -3 to 5? How far is it going? And then always positive. A and B will always be. It doesn't really matter because when you swear it, you're going to get positive answers anyway, but yeah, just to be certain. Yeah.
So, have to do B and C, right?
Yep.
All right.
Super good. Yeah, that's right.
And also, we need to use it for y. If something is negative, positive, could you just add the absolute value of both of them to distance from that?
Yes. So, yeah. What you are looking at is called or what you're thinking of is called the triangle inequality. It's the idea that, and this works for a couple of things, the idea that the absolute value of A plus B is bounded by the sum of the individual absolute values. So it's not a true equality. You can't like distribute the absolute value because you can imagine if I have two positives and I'm taking the difference, then that's going to potentially be, less. But there is an inequality that you can get by doing this. And you use it for like proofs and real analysis, and it's disgusting and awful. But yes, there is an element of that. You just have to be careful because if you're doing it with two positives, it's gonna do the opposite of what you want.
One negative, one positive.
Yeah, it's always gonna be, it can be equal, but it can also be less. Yeah. Yeah. Grab the basket. Yes, there. And then you're gonna take the square root of that. Yeah. Yes.
So what is that right so far?
Yeah, that would work. I would probably not plug it into your calculator. I would probably simplify just on the face of it to be more precise. It's an irrational value, so the most precise way you could leave it is just within the square root. Kind of. Well, we'll see. For both of these, actually, it'll be the most precise.
All right. But let's just say.
It'll be correct. Yeah. The way you use the formula.
You can feel better.
You might lose 1 point because it's not technical. Yeah, what we're gonna find with a lot of this is plugging into the calculator is gonna be more. Because we're working with a lot of square roots, and a lot of square roots gives us irrational values that the calculator approximates, but doesn't give us exactly. And so we need to be able to kind of manipulate these without simplifying the square roots. We'll find. Okay, let's take a look at what we've got here. For A, what is our x displacement? 3. What is our y displacement? 8. And so I get the square root of 9 plus 64. Make sure, very, very important, that you are squaring, adding, and then taking the square root. Very, very important order of operations here. And so we should get the square root of 73. And then for C, what is our x displacement? X, you can do it in either order. For C?
Oh, C.
Yeah. Very good. And so in this case, we get that this is equal to. How do you go from 0 to the square root of 5? Yeah. So the square root of 5 squared is just going to be 5. So a squared is just 5. And then the square root of 3 squared is just going to be 3. Which we could do stuff with that, but I'm fine. So square root of 8, perfectly good. Questions about our distance? Which is again really just Pythagorean. Feeling okay? Not too bad. Okay, I will mention this while we're here. This always gets lumped together and it shows up every now and then. It's not particularly interesting and it doesn't really tie well in with distance formula and circle formula, which we are going to see are really just applied versions of one another. And that is the midpoint formula. If I'm trying to find the value that is perfectly in the middle of two other values, you're just going to take an average. Right? If I have one person who scores a 90 and one person who scores a 70, what's my class average going to be? An 80. If I wanted to calculate that numerically, what would I do? Add them and divide it by 2. Okay, we're going to do the same thing with the x values to get the x coordinate of our midpoint. We'll do the same thing with the y values to get the y coordinate of the midpoint. So it's very literally just an average of our x's and an average of our y's. Tinker with that with example 2 if you want to on your own time. I'm not particularly interested in spending time on this. Cool. It's a good thing to know, right? But like, again, that's something that we kind of intuitively do. What's perfectly in the middle of 4 to 8? 6. How could we show that computationally? 4 plus 8 is 12 divided by 2. Okay. The actual like thing that we are after here. Why are we talking about this into this entire unit on trig, leading into this entire unit on circles? And that is because the circle formula and the distance formula are actually exactly the same formula. Very, very fun. Very cool. So let's consider a circle. And we'll look at a specific circle first, and then we'll make it more generic. Let's say that this circle is centered. I did centered at the origin before, and that was fine. Let's say the circle is centered at the point 1, 1. And we'll give it a radius as well. Why not? We'll say that the radius of this circle is 3. I've made my drawing task a little bit harder than I did before, but yeah, we can cheat kinda. Cool. Okay, let's talk about what this radius actually means. So if I were to be focusing on a point, so if we're talking about like what the circle actually is, we can notice that the circle is really a collection of points around the center, right? The center is not a part of the circle. It's a feature of the circle. It's not a part of the circle. The circle itself would be like this point here, and also this point here, and also this point here, and also this point here, and every single point kind of around this disk that we have. And what is going to be true about the relationship between any of these points that I could pick along the circle and my center? they are all fixed at a distance of 3. Regardless of where I am on my circle, I know that this distance is always going to be 3 because it's a radius. And so a geometric way to think about circles is this like nice uniform shape that's got like an infinite number of axes of symmetry. That's cool, I guess. An algebraic way to think about this shape is to instead think about it as a collection of points that are a fixed distance from a point that we denote as the center. So our actual like definition for a circle is going to be a lot more aligned with this idea. All points that are a fixed distance r from a center. And that center we generally denote as h comma k. Or transformation friends. Go figure. Okay. So we could kind of plug into the distance formula all of this information we have. According to the distance formula, we could say that our radius, or our radius squared, or maybe rather according to Pythagorean theorem, we could say that something along the lines of x1 minus 1 squared plus y1 minus 1 squared is equal to 3 squared. And then for the distance formula, we like took the square root of both sides. Although actually in this case, that's just going to make things look a little bit messier. So okay. Okay, now we've talked, this is specifically to go from the center to this point on the edge of the circle. That's what the x sub 1 and the y sub 1 means. I could use an x sub 2 and a y sub 2, x sub 3, y sub 3, x sub 4, y sub 4, x sub a billion, y sub a billion to denote a billion individual points. But our definition for our circle is not referring to a specific distance between one particular point and the center. It is every single point that matches this kind of criteria of being a radius away from our center. And so rather than referring to this as a specific x1 and a specific y1, we denote these as a generic x and a generic. Kind of similar to how we were doing how we generated the line formula, how like x2 minus x1 was like a specific x minus a specific y, but x minus x1 was a generic x minus a specific y, and that lets us generate an entire collection of points rather than just talk about one specific relationship. We get the exact same thing here. And then, of course, we have this specific center, and we will have a specific center with what we are working with. But, you know, the center doesn't need to be 1, 1. Of course, we could be looking at any center at HK. So what we often see is this formula of x minus h squared plus y minus k squared is importantly equal to not r, but r squared. And we don't take the square root of both sides. If we were to take the square root of both sides, notice that we would literally get this. Or if we squared both sides of the distance formula, okay, we get. So they're the same thing. It's all Pythagorean theorem. It's all the same notion over and over and over. This is a nice freebie. Couple of free points on the ACT that you guys have next. It invariably shows up at least like twice. So. Okay, that's, yes. Yeah.
ACT, like I know a lot of teachers have told me that ACT and SAT are similar, are a lot similar, so can I just do digital SAT and math and reading?
Sure.
On Khan Academy?
Yeah, that'd be fine. We did on Friday, before fall break.
Also, one more quick question.
There's a practice test and a solution set that are posted to Schoology.
Oh, yeah.
Yeah, I would highly recommend taking a look at that.
I'm doing pre-calc right now. But previously, if I have done John honors geometry, algebra 2 honors, and prop and stats, should I be am now doing since I'm doing pre-calc?
You should have seen most, I would say most of the content that's on the ACT. Most, no, maybe not, but most. I think there's there's a practice ACT and then the PSAT is something different. So you're gonna take an ACT on the next Tuesday, yeah. And it's the same day that the seniors are taking the normal ACT. Yeah, it'll be a practice ACT next week, next Tuesday. Now the real one you'll take in the spring. Yeah, it's because a lot of people a lot of juniors have not taken algebra 2 yet. So the idea is let them finish algebra 2 and then they can take the ACT, but like finish algebra 2. Rather have it count, right? But it's free.
Yeah, I didn't know how it worked, like.
Yeah, I think it's summer.
Oh, that's right.
I still do the better.
It's supposed to be a sophomore year.
PI 89, but 84, yeah, 84, 83. Yeah, no, 89 is the only one that's banned, and that can do like crazy stuff. Like that factors for you.
You can still do that easy one.
Yeah, you have to like, and I guess at that point. Yeah. I had a physics test where I did that, where I just like forgot a calculator. I was like, all right, we'll just run. Yes. No. All right. Okay, so this is lovely, and this is where I stopped last year when I did this. Because it's this is nice and compact, and why would I be mean and give it to you in any other way? And it's because the SDC is going to tinker with this just a little bit more. This is actually our goal. This is like what we want to see. And sometimes it's not always that nice. I would say this is like a great example of where a slightly unsimplified form is actually like way more ideal and conveys a lot more information. But what if I gave you the quote unquote simplified form or the standard form? Well, that would certainly suck at me, wouldn't it? And ultimately is what we're going to do. So we're going to do something very similar to when we did vertex form. Think of this as like almost like what we did with the vertex form and the quadratic, kind of moving back and forth between those. We're going to do something very similar here, just to kind of get a feel for how we can identify what H and K are supposed to be. How could we like unentangle R from all of this? Okay. So in order to simplify this, what should I do? How should we make a mess of this very nice formula that we have? Well, okay, so we could square root everything. We're not going to be able to like clarify what's going on here. Notice that this doesn't simplify at all. Let's just work on our left hand side. What can I actually like? X minus h squared, that's all nice and compact. How could I make it less nice and less compact? Yeah, Yeah, we can do the Punnett square and do x minus h times x minus h. That's, I mean, an idea. X squared minus 2hx plus h squared. Okay. Sure. Okay, similar question. What could I do with y minus k? Exact same thing. You can do the Punnett squares to confirm that I'm not lying to you. But this should be y squared minus 2ky plus k squared is equal to r squared. And there's an issue. It's kind of a funny issue that arises again from this idea of simplification, and that's that this h squared and this k squared are like terms. So they're not going to be given to you as h squared and k squared. They're just going to add together. They combine. There's no x, there's no y. Those are just numbers. It's whatever the x variable is squared of the center, whatever the y variable of the center is squared. If you look at, for instance, example 3a, which I have slightly left unsimplified. Actually, it's made it a slightly worse problem. This 25 is meaningless in terms of h and k. This is h squared plus k. It's the two of them added together. And so looking at that 25 to try and figure out what the center is actually a little bit tricky. To make matters worse, if I wanted to be really mean, I don't know, look down a problem, I could subtract r squared from both sides, and now h squared plus k squared minus r squared has all combined to make this minus 12. That becomes really difficult to approach. It becomes really. So what we do instead, we're going to have to look somewhere else in order to figure out what's going on with h and k. In particular, what is the only other place that I could look that would give me an idea of what should be going on with h? H squared is not going to be very helpful because that's combining with the k squared and the r squared to make a mess. What could be helpful here, though? H squared is off the table. Where else is there an h? The linear x term. So if I can't use the h squared to figure out what h is, because it's mixed up with all this mess, we'll use the negative 2h. All right, we'll just look at the linear x term, whatever that coefficient is, it's negative 2h, divide by negative 2. Similar question, if I can't use k squared to figure out what's going on with k, what am I going to have to use? We'll use negative 2k. Okay, that shouldn't be too bad. Let's try that. So we said here our linear x term is actually negative 2h times x, and our linear y term is negative 2k times y. Okay, great. What is the value of h? What is the x value of my center for 3a? Yeah, it's going to be negative 3. Just divided by negative 2. Okay. If I have that negative 8y is the same as negative 2ky, what is my value of k going to be? Negative 8y to negative 2k is positive 4. That's cool. The tricky bit then. The tricky bit that we are going to find here. And here I didn't make this quite as convoluted as I could have. I was kind of nice and I left the r and the h squared and k squared separate here. What is h squared? 9. And in this case, what would k squared be? 16. Notice that my h squared and my k squared are what is responsible for this 20. Right? Plus 16, that is combining and creating this 20. Yeah. So from our multiplying everything out from the Punnett squares, which you can do to confirm if you would like, we said that this circle formula is the same as this whole string. And the thing to notice is that while h squared and k squared are not necessarily all that useful on their own because they combine, I can still find h by looking at my linear x term and dividing the coefficient by -2. And I can find k by looking at my linear y term and dividing that coefficient by -2. Positive 6 divided by -2 gives us the -3 value for h, and -8 divided by -2 gives us the positive 4 value for h. And so we can parse apart, or splice really, what we see here into x squared plus 6x plus 9 plus y squared minus 8y plus 16 is equal to 4. And what's really, really nice is we can then factor each of these two quadratics, but we don't even need to factor them because we already know what they are going to become. We know that this is going to become x minus h squared. And we know that this is going to become y minus k squared. And I have set this up deliberately so that we can very easily just look at this and tell what are h and what are k. And so what is the center for this particular circle? We found at the very start. That was like the first step. -3, 4. Yeah, ready.
Why is it x?
Always x minus h, always y minus k. Because we're taking a look at the x displacement, which required subtraction. So thinking back to that one-dimensional difference, it was always 7 minus 2 in order to figure out the distance between those. X minus h. H in this case being -3. Could you write that as x plus 3? Sure. I'm writing it as x minus -3 to make it really clear that the x value of the center is -3. And then what here would be our radius? Be a little bit careful. Yeah, it would be 2. Square root of 4. Okay, you'll notice we didn't really do that much here. We just kind of found the h and found the k, and then made the observation that the 25 can split apart in this way that we were kind of anticipating it to split apart. What becomes a lot trickier is if I were to combine hk and L, or if we didn't know what r was kind of going. that becomes a lot harder. So first and foremost, questions with 3A. Let's try the exact same process. Our goals are really the same. We're trying to make our quadratic look like this so that we can factor it in the way that we know that we can. We need to, in order to do that, figure out what h and k are supposed to be. So this is, we said, negative 2hx. We've got negative 2ky. What are my values here of h and k? What's a little bit weird here? So say again. H would, okay, notice we don't have a linear x term, right? So compared to A, where there's this 6x, there's nothing here to compare it to. Well, what's going to make, what could I multiply by to make that linear x term go away? Absolutely correct. H in this case would be 0. H squared then is going to be also 0. Cool. Okay, cool. What is k going to be? Positive 2, and k squared is going to be 4. Okay, we actually could, there are a couple of ways that we could go about solving for kind of what we are trying to set up here. For instance, we could look at this and say, I know that this is h squared plus k squared minus r squared. That's a valid way to approach it. Then you could just let me know what h squared is, we know what k squared is. I can just look for what r is going to be. That's actually probably the most straightforward way, but I'm going to do a way that I think works very, very cleanly. And I think is more akin to what is often shown for this. What I'm going to do is I'm going to make it so that all of my constant terms are on my right-hand side of my equation. So I would add 12 here to both sides. Actually, do I even want to do this?
So it's nice.
Sure.
Negative 12, like, h.
So that is h squared, k squared, and r squared all combined. Well, so h squared and k squared are added and r squared was subtracted over. So, okay, so one way to do this, and I think a really good way, is to note that negative 12 is equal to h squared plus k squared minus r squared. What is h squared? 0. What is k squared? So subtracting 4 from both sides, I get that negative r squared is negative 16, and that r is 4. That's the way I was not finding myself kind of drawn to it. That's good. Not the only way. Actually, what I was going to do is I was going to shift the 12 over, then I was going to add 0 and 4 to my left-hand side. And if I'm adding 0 and 4 to my left-hand side, I have to do it to the right-hand side as well in order to keep things balanced. You get the exact. Okay, so we have our center, we have our radius. Let's go ahead and give I would say the standard form equation, is that one standard form? The good equation for our circle. So if we are centered at 0 and 4 with a radius of 4, what is my equation for my circle going to look like? So it's centered 4. So the radius we solved for, this was 4. And so what is my circle equation going to be? You do x minus 0 squared, but x squared, that simplifies, right? So x squared, which note that that is equivalent to x minus 0 squared. Okay. Y minus 4 squared. And what is that going to be equal to? 16. Yeah, that's just Pythagorean theorem. Yeah, notice that the x displacement, the x distance is between 0 and whatever x is. So 0 minus x or x minus 0. And then the y displacement is between whatever y is and 4. Pythagorean. Yeah. So notice here that our, oh, no, you're right. It should be 2, not 4. Yep, good catch. Yeah, I used k squared rather than k, but you're supposed to use k. Sure. Yeah, y minus 2 instead of minus 4. My bad. Questions with distance formula and circles? Feeling okay? Okay, if you guys would go ahead and get out your laptops and go to Pearson. Something that I have been saying that I would like to really emphasize for this particular classwork is that I have been and will continue to post kind of like advices on how you should be completing these, like what my recommendation would be for what to have worked on. I will continue to have that be, the extra credit on the quizzes. The 4.1 through 4.3 classwork, this is largely, I will say, a lot of this is like very, very snappy in terms of how fast some of these problems will go. So it is not as onerous as it is going to appear. It is 38 problems long. And the quiz on this I am projecting to be next Monday. So you have a full week in order to work on it. I'm giving you guys, we've got about 10 minutes, a little bit less, in order to get started. The completing the square problems, which is what we did right here at the very end, you can find those as, I believe, 7, 8, and 9 on this classwork. If you would like to test yourself and get a little bit more practice with that kind of with that process. So those are good ones to attempt during this time. But of course, you guys are more than welcome to work on any of the questions 1 through 9. And then if you have completed 1 through 9 by class tomorrow, you'll get that bonus point. Yeah. I have to adjust the quiz because this was originally Unit 1, and now it is